Okay, well, I'm gonna leave you to it, and I'll text you if it works or whatever.
All right. Okay.
All right. Okay, looks like you're good to go. All right, see you on the other side, Bach.
Okay. Okay. Can everyone hear me? Can anyone hear me at all? Someone please say something in the chat if you can hear me. Hello. Damn, just like no viewer right now. Okay. Okay, so we are currently having 3 people on the stream. That's pretty nice. Hello, Sanjeev. Okay, can everyone hear me right now? If everyone can hear me right now, just like type something in the chat, like whatever you want to type. I don't know. Hello. Okay, Sanjeev can hear me. That's nice. Okay, Joe, are you there? Yeah, so on today's workshop, Joe's gonna help us with the workshop, like answering the question in the chat and stuff like that. So yeah, Joe, let me know if you are up and ready. Hello. Okay, Joe is getting in. So we just have, yeah, I'm sorry guys. Like we just gotta have to wait for like a couple minutes. Yeah, here's his first. Okay, he's here. Okay, so I guess we are ready. We're ready to start then. Nice. I'm so sorry for like starting workshop late today. I just woke up because like yeah, my time zone just 12-hour difference for what most of you guys are currently are right now. So I'm so sorry for this delay. All right. Okay, so we get started. By the way, I don't think there's a way for us. Or, I don't think there is a way for us to take a chat. Because when I stream, it's going to be in a full screen. So, yeah. Okay. There's so many things getting screwed up today, so I'm so sorry. Let's just start. Can I ask something? Wait, restore chat. Okay, so Joe, can you like forward every single questions that everyone may have to me to the Slack account? To my just type as a chat or something because I cannot see a chat when I'm streaming. I'm sorry. Yeah. Slack. Yeah, just forward every single question to like the Slack uh to the Slack account. Like as like you send me a chat something. All right, yeah, you see in my in my in my in. All right, thank you. Nice. Okay, so we can finally start. We are 20 minutes late, so that's a bit bad. But okay. So, okay, welcome everyone to the first workshop of the Introduction to NLP series. And this is brought to you by AIS Technology, coordinated by Nguyen. So in this series, we take a look at the field of NLP, starting at from an overview of the field itself. The first thing we do in NLP, which is representing text, going through like deep learning techniques in the NLP, and then we finally explore powerful pre-trained model. So today we are here for a quick look at NLP and learn the magic of turning words into numbers that computer can understand. So before we intend this workshop to be your introductions to NLP, we shall start off looking at an overview of NLP. So how can we define the field of natural language processing, or NLP? NLP is an interdisciplinary field concerned with the interaction between computers and natural human languages. So what we mean by natural human languages are like something like conversations, spoken language, and written language, as in books and news, and also English as well as our international language are also count into this group. So we usually have some combination of things like written English or like conversational Chinese. So now that we have answered the what question of NLP, we move on to answer why of NLP. So where can we find NLP in either industry or in our everyday lives? So one very useful task of NLP is conversational agents, also called chatbot. If someone here have seen like 2001: A Space Odyssey, then they will know that HAL 9000 is a very capable AI. He's like he can speak and understand perfect English and even like comprehend emotions in the speech. And also something that's more close to everyone here is probably something like Siri, a virtual assistant featured in most Apple product. And it is available in your pocket. And it is a form of conversational agent. It's very fancy way to say chatbots. Okay, another popular language-related task is machine translation. So machine translation is like nowhere near being perfect, but they are also nowhere near being simple. So we have a model that looks like this, translating language in like a really slapdash way, but it is actually a model that looks like this, costing like a lot of computational resources, and is hosted on like a really big corpus of data. So we improve language models and more data, machine translation is gradually getting better. Okay, traces of NLP in your everyday life can be found everywhere. So from smart home accessory to automate answering service. So if you call the bank and you hear like a bot answering your question and like hearing to what you have to say, redirecting you to correct people, that's an application of NLP. So even like for Siri inside your pocket phone, something like that, NLP have been powering like many aspects of our everyday lives, and like many technology corporations consider NLP development a priority. So the field of NLP is not typically divided into subfields, but rather that NLP tasks that address some of the goal of NLP. So that's how the scope of NLP is defined. Some NLP tasks have direct real-world applications, while others serve as like subtasks that are used to aid in solving larger tasks in NLP. So in NLP, we typically have like tasks that are like basically the end goal of NLPs, but we will try to address these big tasks like smaller tasks. So common NLP tasks include post tagging, part of speech tagging, which is basically just determining which part of a sentence is a noun, a subject, etc. We have text summarization, which is basically just summarizing text. And it's typically very helpful for providing abstraction for libraries or providing like product description on Amazon for books, of course. And finally, sentiment analysis. So sentiment analysis is basically identifying the polarity of a piece of text. So if you have like a piece of text, right, you want to know if it's negative, neutral, or positive. And it is incredibly useful for identifying public trends and for product marketing. Okay, so now that we have taken a look at like a broad overview of NLP, we will start to look at something that most of you guys are going to take a look at. Like the main focus of today's workshop is like an introduction to word embeddings. All right, so word embedding is like kind of like an abstract term right now. So it's a form of word representation. So the first question is, why do we even have to represent words, right? What's the point then? So why image data can be effectively and efficiently represented by pixel values. So if you have an image, you can just decompose them and like have every single pixel on the image being like a value, like an integer, right? Or a set of 3 integers, which denote the RGB values of that pixel. But for text information, it's not like capturing the meaning of the body of text, like an essay or a book, right? It's not that simple. So therefore, we must find a way to represent the meaning of a text body, starting from representing the meaning of individual words. Then, how do we represent the meaning of a word? Or in other words, define a word? So the meaning of a word can be defined in a very practical way, which is its real-world usage context, or how we understand a word in our newspaper and in our conversations. So in this case, we can see that a word bank has 2 different meanings. One is talking about a financial institution, and the other is talking about a geographical feature. In this case, we can see that a word bank are being used in 2 different situations, in 2 different contexts. And that's how we define the word. And so one natural consequence of that is that words that occurs in similar contexts tend to have similar meanings. So, and also over time, the usage context of a word can change, and so are its meaning. A word that's really popular nowadays is yeet, and we don't really know the meaning. We don't have a clear meaning to that word like 10 years ago, right? But it suddenly became a word that kind of like define how you just throw something, maybe quite a bit violently, or even throwing something like it doesn't need to be an object, it can be your classes. And so the current best model for kind of like defining the semantic of these words and can effectively deal with these kind of word meanings, we call them the vector semantics model. So what are vector semantics? So vector semantics is a practical way to represent words based on the real-world usage context. Vector semantics is like a combination of 2 intuitions, the first one being the distributionalist intuition, a method of defining a word by counting what other words occur in its environment, in its context, like around it. So in this instance, right, I just have pointed here, we can see that the word love here, the word love here frequently occurs near the word I. It's like 2 times, like almost the highest number in table. And so that's our distributionalist intuition. The second intuition is the vector intuition, in which we define the meaning of a word as a vectors, a list of numbers, and a point in n-dimensional space. So this might sound a bit abstract, so I just take a very specific example here. We have a word rocket, right? So here we have a word rocket, which is defined by 3 attributes. The first one is the wings, so it doesn't have wings. So we will say that it has 0 wings. Skies. It's kind of like, okay, rockets are in the sky, and you're supposed to fire it. So it has a lot of sky. We have 4 sky for it. So we have 4 here. And for engines, the rockets basically just powered by engines. So we have 2 of them here. It's defined by 2 of engine. And that is what we call embeddings, vectors for representing words. Because the word is embedded in a particular vector space. Words with similar meanings tend to be really close to each other in the vector space. So we can see that words are like kind of similar, right? So drones already in the same domains with rockets are really close to rocket here. So now that we have our vectors, how do we create them? We move on to learning about embeddings algorithms. The fundamental ideas behind embeddings is representations of word similarity. So how can we represent word similarity? Because we define each word by the context around it, we need a record of the context of each word, right? We need to know what kind of words occurs around the word that we are looking at. And so we have something that do just that, called the co-occurrence matrix. The particular types of co-occurrence matrix that we care about today is the word matrix, which recurs the frequency that 2 words co-occur within the same context in some training corpus. So the context of that training corpus of that word can be as large as the entire document. So you have it occurs in the same document, in the same story, right, or in the same book. Or more commonly used would be like a certain window around the word itself. So for example, like two words before the word or 2 words after the words. And we take that windows out to be the context. So here are the co-occurrence vectors for 4 words in the Wikipedia corpus, which 6 hand-picked dimensions. So in reality, it's not going to look as nice as this. We just pick like these 6 dimensions because these are like what we want to demonstrate here. So note here that the word digitals is really high into other words, computers and data, right? And they are really closely related word to digitals, as you may know. So note that the real vectors will have many dimensions because we're comparing each word to every single other word. We're counting them to every single other word in the vocabularies. So how many words you have in the number of words that you have in the vocabulary of training corpus, we have that many vector dimensions, right? So imagine we have like 10,000 of them. We have 10,000 of vector dimensions, not like 6 or something like that. But we'll take a look at that later. So now that we can represent word similarities, how can we measure the degree of similarity between 2 words for our embedding purposes? So to define the similarity between 2 words, we need a way to take the 2 word vectors, which were generated by the matrices that we just take a look at, and calculate a measures of similarity based on these vectors. So when we talk about similarity between 2 vectors, right, one that naturally comes to our mind is the cosine of the angle between them. So it is a variation of another similarity measures that's really typically used in NLP called the dot product. So you just take the dot product of 2 vectors. You have like done any algebra at all. This probably kind of sound familiar to you. But like, yeah, so what we see here is the formulas to calculating the cosine between the cosine of the angle between two work vectors, and that still seem a bit abstract. So I present here a more intuitive example. So we can see that the word vector friends and the word vector Italy here are like quite similar, right? So the angle between them are really close to 0, and the cosine is like close to 1 naturally. But like on the other hand, we have the vector ball and crocodiles, which is like not similar, obviously, and they are like they're having an angle that's like close to 90 degree, and thus the cosine is like close to 0. So the pattern that we can see here is that like to more closely related these two vectors, right? The smaller the angle between them, and the smaller the angle between them, the smaller the cosine values. So well, cosine values typically range from 0 to 1. They cannot go from below 0 since our word frequency is not negative. And we can see that the higher the cosine values, the more similar the words are. So we already have here a similarity measure. Okay, so now that the kind of word vectors we've been looking at are some examples of sparse word vector representations. So what exactly are sparse vector representations? A typical co-occurrence matrix looks like something like this, right? With most entries being zeros, since each word can co-occur within a few number of other words in the entire vocabularies. So, and as a result, a typical word vectors extract for the matrix will look like this, which is kind of gross because you can see that the vector is really big, right? But non-zero elements are few and far between. And sparse representations are troublesome for this very reason. They increase the feature space of the machine learning model and ultimately increase the model complexity and chance of overfitting. And trust me, if you have been like in machine learning for a while, you don't like overfitting. Even when you start out, you really don't like overfitting. And more importantly, sparse vector may leave out important word meaning informations. Remember that the goal for us to represent word as word embedding is to capture the informations, like the meaning informations of the word itself. So consider the case of one hot encoding where each word vector is positive on the word's unique index in the entire vocabularies. So here we have like each word, right? We are encoded with like a single vector, like a single values of vectors. So for example, cat is a vector 1000. Dog is a vector 0. I'm sorry, my pointer is switching out. Dog is the vector 0100. So you can see here that each word is encoded by a unique way, but it gives absolutely no information on how the word cat might be related to dog or any other animals, right? Because all you know is, oh, it exists as a thing, but how it is related to others. Okay, now that we have learned about the limitations of sparse representations, we move on to take a look at dense vector representations. Yeah, it's the opposite of sparse vector representation. Dense vector representations is a form of representations that relies on short vectors, so it's like 50 to 1,000 unit long. That's what we call short, because the long sparse vectors are like thousands, like a couple dozen thousands units long, right? So that's way longer. And they are also really dense vectors. So most values in vectors are non-zero vectors, meaningful values. So more than merely condensing meaningful word similarity information, dense representation can be learned directly from text. And that's what we really care about. We can learn this kind of word meaning. So if that's correct. If angle is 0, two embeddings are really similar, and the cosine then will be 1. You got it. So let's continue. So dense representations can learn the semantic information directly from text, right? And it can represent them in the form of closely related low-dimensional vectors. One very popular dense representations method is called word-to-vec package. You probably heard that before if you read some stuff about NLP. And it is a package of embedding algorithms containing two embedding algorithms called the continuous backward and the skip-gram method. And today we'll take a closer look at like the skip-gram negative sampling method. It has a very fancy name. So the intuitions of word2vec is that we train a binary classifier to predict if sad is likely to show up near cat. The classifier is incredibly simple to train because we can just have the running text as the training corpus. In his sentence, right? In particular, if you want to take the training example for cat, you can just take the word near it here, like sat and t, as the supervised classifier model label as positive sample, right? And we can use that in the supervised learning algorithms. And so the intuitions of skip-gram is: first, we treat the target word and the neighboring context word as positive samples. Other words in the lexicons are randomly sampled to get negative sample, right? In other words, you just take every single other word that we have not seen yet in our positive sample as negative sample, and we can just take them from the vocabulary. And then we use logistic regressions to train a classifier to distinguish these two cases. And finally, we use the hidden layers regression weight, also called here the embedding layers weight, as word embeddings. So you can see here in the network, it's embedding layer here that we will take as our final word representation. Okay, so now that we know the intuitions of this of skip-gram, we actually just jump straight into like coding it right now. So I'm hope like everyone prepared for some coding right today. So okay. Excuse me, I just oh sorry, it's spoiler. I post the link to the coding template here so everyone can take a look at it. Why is my camera on? Okay, that's a bit weird because every time I try to go to the borders of the window, it just glitched the hell out of me. Yeah, you see. Alright. I just have a link here, so just let me copy it, please. Let me copy it. Dude. Okay, copy link address. So I just posted in the live chat. Yeah, so I post the link to a number in live chat. Everyone can take a look at it. Okay. Yeah, for some reason my mouse just glitching out, and it's kind of annoying. It is my first time streaming on OBS, so I'm having more problem with this. Alright, I open the notebook here. Okay. So we all know that the first step to creating a skip-gram model, right, is that we have to create the training data, and that's what we call the skip-gram sampling method. And so here we have like a notebook. Here I have like a notebook for everyone. It's like a template notebook, so we can take a look at that. I try to provide some intuition on it along the way with this. I'm sorry. Okay, that's actually annoying. Next time I'm just going to stream on you with something. Okay, all right. Okay. So the first step, if everyone's already have the notebooks up, yeah, you just open it. Okay, so we connect. First thing first, we'll connect to the server. All right, now that our notebook is connected to a host, we take a look at what kind of libraries do we import for creating the training example. So this is like an isolated notebook from the main notebook where we train the actual root-to-vec vectors. But here we take a look at how we generate the training sample first in isolation, so you guys can have a more like intuitive understanding of how it works. All right. So here we import like IO, right? Iter2 stuff with that, really standard stuff, libraries, standard Python library. And then we improve, because this workshop, we're going to use TensorFlow. And one thing that just come naturally with TensorFlow nowadays is the Keras processing libraries. It's a very, very helpful processing libraries. So we we import some of them here to use with processing our text. So here we import TensorFlow TF. We just have something called tokenizer. We'll see how it works, like why we use it later on. It's a sequence thing, so that we can pass sequence. It's not really necessary. Text to word sequence and the skipgram itself. I mean, we just have a method called the skipgram method for generating sample. All right. So the first step, we are taking a look at one particular example sentence. The quick brown fox jumps over the lazy dog. Everyone probably seen this in Word something. So the first thing we do here is vectorizing the sample sentence. I try to provide more intuitive view of it, so I just have this guy up right here. Okay, so what we want to do when we vectorize, what we meant by saying that we want to vectorize a sentence. Okay, skipping the quick brown fox jump over lazy dog. All right, so for example, I have a sentence like, I am a cat, right? Okay, so if we have a sentence like this, the computer will probably not going to understand it by itself. So what we do, the first thing is we vectorize this sentence. Vectorizing consists of two steps. First thing is we split the sentence, and second is that we tokenize the entire sentence. So the first thing first we do. So what we do here is tokenizing, right? So for this sentence, right, we generate a set of token, and to generate this set of tokens, we need to know what kind of words are in this sentence in the first place. So to do this, we just construct a library, a vocabulary, which is basically like something that translates from word to numbers, right? So I will be like 1, it's like hash map. M will be like 2, will be a 3, and cat will be a 4, right? So what we meant by vectorizing this is that we take this sentence and we split it into tokens, a sequence of tokens. So we have an array here, and I will be 1. M will be 2. We're just translating it from the vocabulary here that we have. So each entry of this thing, of this vocabulary, will represent like a single unique word in the sentence. So if you have sentence that kind of like have overlapping word, it will still like be one entry in this dictionary vocabulary in 3, 4, right? So this is what we will feed to a computer by tokenizing a sentence. And that's about what we do here. If someone have a question, ask it now. Everyone still with me so far? All right. Oh, sorry. Okay, so okay, here we go. So here to tokenize a sentence, we have sentence here. We turn it from text to word sequence, and we feed a tokenizer on it using the Keras tokenizer. And after we feed it, I just run the code so far. Run before. Yeah, don't worry about it. You can just copy the drive to save a version of it to yourself. Now that we feed like a tokenizer on it, we can check what here we call the word to ID dictionary. And so we take a look at how this dictionary like tokenize the sentence here. And we can see that the dictionary is assigning each word in the sentence a unique ID, right? One thing to note about the Keras tokenizer is that the more common a word is, like the smaller the integer denoting it will be. So you see that the word here occurs 2 times in the sentence, right? So it's the most common word, and it's also the word with like the smallest ID. And also we create an inverse vocabulary so that we can translate from numbers to words. And to factorize this sentence, right, we can just run a simple loop with the dictionary comparing it, and we'll have like the sequence of like the vectors here. And this is a number of representations, the tokenized representations of our sentence. The quick brown fox jumps over lazy dog. All right. So now that we have like a sequence of numbers, what do we do with it, right? Well, funny thing is, Keras library has something called the skipgram function that can generate us like a set of skipgram. And if we switch to this slide, right? If we switch to this slide, we can see how the skipgram function itself works. We have like a sequence of words that we feed into a skipgram function, and given a context window, right? So for example, like 2 words before the target word and 2 words after the target word, it will generate like some training sequence to it. And here you can see that it is going through this sentence, I like play football with my friends, gradually, and generate these like training instant, right? So you have I being the target word and the 2 words near it after it, like playing as a context word. And that's how the skipgram function just basically works. And so we just take a look at what kind of parameters it requires us here so that we can use it. Okay, so we need a sequence, a vocabulary size, a window size, a negative sample rate, and whether we want it to be shuffled or not. I mean, I don't care. But so what do we want? So to generate that, we'll probably start doing some code here. Anyone have a question so far? Okay, no question so far. Okay. Yeah, just wait for like a minute to. I just have something ready so I can have things that easier with you guys. All right, so back to our notebook. Here we want to set like, as we see before, right? We want to set like something called a context window size of 2. And we start by generating what we call the positive skipgrams. We just leave like the second entry here blank because we don't want to take the second output of this function. tf kras pre-processing sequence skipgram is a pre-bit function. Very nice. So here we already have the first thing first that we need to fill out the sequence thing, right? And we can see that the sequence is just the example sequence that we generate from the last step. The second variable that we have to fill out is the vocabulary size. Vocab size. Vocabulary. And can someone here give me a quick prediction of what we want to fill for the vocabulary size? I just for our live stream here. Yeah. Anyone here wanna guess what do we fill for our vocabulary size? Like what is the scope of like the number of the words that we're considering here? Remember that we have a tokenizer and we have dictionaries of other words. So what is like the length or like the size of vocabulary? All right, no one's answering that. So okay, it's a really simple one. So you don't have to worry about it. It's just the vocab size that we already denote here, right? So we get the length of the tokenizers and we just put it here. Because tokenizer already encode every single word in our vocabulary. Okay, so for window size, we already set it up. Up there, so we just equal it to window size. And lastly, we have negative sample. Note that we just set this. Yes, we have a question. Let me check. The words number in the training sequence. No, it's a vocabulary. Oh yeah. All right, yeah. Joe got it. So okay, so we're just continue on. So for negative samples, we set it to 0 because we are not trying to generate any negative sample from this function itself. It's kind of like really hard to process these kind of negative samples, and we will take a look at creating these negative sample anyway in our distributed way. And here we go. From this mere sentence, mere like 10, like maybe 1, 2, 3, 4, 5, 6, 7, 9 word long sentence, we generate 30 positive skipgrams, right? And that's quite a lot because we're sliding a window over like each span of text of the sentence. So that's how we generate these many instances. And we just take a look at a few possible skipgram. We have the word target word overs, right? And the lazy word is in the context of this word. And also we have a couple other words in the context of other words too. The word on the left is like the target word, and the word on the right is the context word. Okay, so now that we generate the positive instance for the classifier, how do we generate the negative instance for it, right? We need something to balance out the data set because we don't want to have everything to be positive. And so for each for skipgram, for each positive sample, we kind of have like how many we kind of have like how many we kind of think about like if you have one positive instant, we have like 2 or 3 negative instant, right? So it is like this very specific ratio that we just set for ourselves. And so what we want to do here is that we want to right, is that we just want to like randomly sample from like the negative sample the negative samples from the vocabulary. So anything that's not a context word, we just sample it as like the not context word in vocabulary. And so we do that with a function called, we just do it with like a function called the TF random log uniform candidate samplers. So yeah, it's a bit confusing to say, so I just type it out. First thing first, we just set the target word and the context word to the first positive scriptogram for ourselves, right? So we just get the first pair of positive scriptogram and we create like some negative sample for it. And in this instant, we want to create like 4 negative samples per every positive samples. So we have numbers of negative samples set to 4. And because when we use like the functions in TensorFlow, we need to know about the true class of like what is the real context word for this target word, right? We just fetch it from what we generate from the sample where we just get here. So context class will equal to TF. TF, we set a constant here in TensorFlow of the true word or true class. Data type is an integer in set4 and we set it to set11. It is a tensor of size 11 that classifies the correct class for this target word. And we create this negative sampling candidate from here. So we call it a negative sampling candidate. We leave the same to blank because we don't want to get the output to form a function. And we use a function called the log uniform candidate sampler. What this function do is that it takes in the vocabulary and it randomly sample all the words except the word that is correct from the vocabulary. So naturally we have an attribute to this function called the true class, right? So we know what to exclude from sampling sampling the vocabulary for negative sample. And by negative sample here, we just mean that the word that is like not actually in the context of the target word. And we can just have it as a context class. Number of true instant equal to 1. Right. Number of sample, we set it to the number of negative sample. Almost have been error here. We just set everything to be kind of unique. So we have true here, unique, because we want them to be unique. We don't want to have like overlapping sample. Range max will be set to vocab size. We want to sample all across the entire vocabulary, so that's why we set the range max here to the entire vocabulary. And we control the randomness of this sample by using the seed that we set before. And we set a name to operation called the negative sampling operation. Okay, so what this code do, like I just repeat it real quick, is that we sample everything else except for the context word that we got from the positive scriptogram as negative sample. And here we can take a look at the candidate for the first, like negative candidate for the first pair here. So we have 4 words here, right? It just basically pick out a randomly 4 words that's like not the true class of over. So the first target was over, right? And they just pick for these 4 as something is not occurring near over. And now that we already have the negative samples, we try to construct one like training example. Let's see if we have any questions so far. Okay, no questions so far. All right. So now that we have a negative samples, we try to construct one training sample. And here are some code to just do it. So what we are trying to do here, right? I just switch this on real quick so we can have a quick overview, a quick intuition of it. Okay. So now that I have a pair word, a cat and cute, right? So this is the target word, and this is the context word. And because this is like the true class, like the positive skip grant sample, we have like a couple of like negative sample, which is cat and dog, right? Which is basically is negative because why would you have dog in neighbor of text of cat? Truck for some reason. And what do you call hen, right? Okay. So here is our positive samples and our negative sample. What we do here now is that we have a true class. We have target word, which is cat, right? We feed it to the classifier, and also we feed it a vectors of like context word here. And the context word here is just like a training sample, which is cute, right? And the 3 other negative samples. And what the classifier try to do now is that you generate like a vectors, right? Classifying if this word is going to be likely to occur near cat. And because we all know that cute is a real class, it will classify something like, we have like 3 negative sample here. So we have something like 1, 0, 0, and 0. And that's one of our training sample. And in this skipgram code, we just have here constructing vectors of negative sampling candidates. We concatenate like positive context word with this negative sample word. We label them, so 1 for the positive one and 0 for all the negative samples, and we squeeze them to some of these like global vectors. If we run this code, we take a look at the context and corresponding labels for our target word. Right, so this target word, and these are the context word that we generate. Lazy is the true context word, and the other guys are like the fake one. So the classifier correctly classify these guys, right? So be 1, 0, 0, 0, and that's one training sample. And so what we feed to the model itself. We feed in a target numbers because we are denoting every single word as like an integer, right? So we just feed the model integers and a context vector, right? And the model will try to generate this label, which label if this word will be in the context of the first word or not. Okay, now that we know how to construct a skipgram sample, a skipgram training sample, right? Now that we know how to construct a skipgram training sample, we take a look at how we can create the model itself, like the neural model. And so I have this second code, template code, that everyone can take a look at. Here we go. I just post it in the live stream chat. All right. So take a look at this code. Okay. So this is about importing libraries. Let's connect the word notebook first so we can take a look. Okay. So here, the first step is to import some library, right? If we can import some user-defined corpus. Here, for this sample, we just import like 3 corpus here to take a look at. Actually, the only one that we're going to train the model on is the worldpiece.tsc one. But for this code, you can just import your own training corpus to train the word vectors on, even including your essays. So if you want to see how words can relate to each other in your essays, you can just import essay in and check if you're actually using the word as intended. That's one way to use it. Okay, so here this is syntax, just importing these guys, so it doesn't read that. Okay. All right, here. So that we import all these training corpus. We just import the rest of the libraries. As we all know, we import like the text preprocessing libraries, like what we demonstrated before, and we also import some neural library to build our neural network. What we're going to use here is activation layers, standard one, dense, dot layers, so that we can calculate like the similarity between words, right? Word embeddings. That's why we need this dot layer. We need embedding layers. These are very like NLP specific kind of embedding layers, in where they have like it's like basically a dictionaries of vectors. And you can use this embedding layers with almost every single NLP task after this. Even if you don't want to train like word embeddings, you can have the model learning like kind of the embedding representations. That's the most useful the task. And we just create some variable. We already taken a look at how we pre-process and preparing the skill and training data. So just run all this code. And for this one, right, what we are going to take a look at is the worldpiece.tsc corpus, and we are going to generate these word vectors from the worldpiece. I don't even know what it is, but okay. Since we are tokenizing all the word and all the stuff, but we just do it on a larger scale with all the loops involved, right? So for generating, okay, we already got an error. Okay. Okay, so we have a problem. Context concat. So okay, we're trying to generate context concat. What is wrong? This rank of all inputs tensors should match. Context class negative sampling candidates 0. Oh, here should be 1. All right. Let's run the code again. Yeah, because I haven't run all the code here before, so that's why I got an error. Okay, that's weird. I haven't got this error before. Let me try debug this. Let's take 3 minutes. So guys can just take a quick break while I debug this notebook. You don't have to take a look at the code because It's just the same as what I demonstrated before, but I just put it in a loop so that we can do it over all training sample. Someone here has any suggestion? No. All right. This is like a sample sequence of this is like a sentence, but we tokenize it and vectorize it. And what we got here is a sample. And here we are running the code to loop like the skipgram generations that we just taken a look at before. It's gonna take a while, 2 minutes. And meanwhile, we're going to build our neural model for that. So yeah, I have some note on how to create like a neural model, right? So let's just create one from scratch. What we can do here is, instead of using our standard adding a layers to approach to TensorFlow, we use a method called subclassing, model subclassing. And what I mean by model subclassing is that we just define our own neural models instead of having to create a sequential one and just add a layer to it, right? So first thing we do here is creating a new class called word2vet, because that's the model we try, and we subclass that from the Keras model library. And the first thing when we do to subclass a model is that we have to define an initiation to it. So the initiation function looks something like this, right? We just define the init. This is what we will call when we create a model. So self standard thing vocab size is one parameter that we need, and also the embedding dimension. So what the model we attempt to do here is it reduce the vocabulary size to embedding dimensions, which is originally like around tens of thousands to like a couple hundreds embedding dimensions, right? Okay, so just set a name to it, word to vet, so the model can be called dot init. And first, because in his model we have two embeddings type, right? First is target embedding, and second is context embedding. So we want to create like an embedding lookup layers, like here I said before. We can take a look at the function here. So it is kind of like a standard layers with input dimensions and output dimension, right? All these other variables you don't have to care about unless you're doing like advanced stuff, which involves like importing like an embedding layers that you trained before, something like that. So what we're trying to go for here is that we have to define a context, a target embedding layers that encode the target word that we're trying to encode like the target word in training sample. So we create a target embedding layers, embedding Where's the embedding class? Vocab size is basically the vocab size we take a look before. Embedding dimension. Here, so here, we set the embedding dimension somewhere. Wait, where did I set that? Oh yeah, we put it in layers. So okay, so we just have embedding dimension here. Input length is 1 because we only have like one positive instant. No, we just have one target word, right? So the input length is 1 and name to this thing. We assign a name to this embedding layer so that we can extract it from the model later. Embedding. Alright. Self context embedding. Which is the second one we take a look at. We're encoding like every single context word in the second vector we put into a model. So here will be something like vocab size like before. Same embedding dimension. And here input length is equal to num of negative samples plus 1. Why num of negative sample plus 1 here? Because we have like we are putting like in a context vector which consists of one positive class, right? Like the class where the word is actually the context or the target word, and some number of negative sample, which in this case is 4. So that's why we add 1 to a number of negative samples and assign it as an input length to the context embedding. And to calculate the similarity between these vectors, we use the dot layers. Why we use dot here and not the cosine is because cosine is actually a normalized versions of the dot product similarity matrix. But why is this normalized? Because the length of the word vector is typically defined by the frequency of that word, right? So we need to normalize it. But in this case, we don't have to. We can just take a dot product here in our neural model. AIS will be equal to 3 in 2. And we flatten thing to return. Okay. Now that we have defined our the kind of layers that we're going to use, we're going to create. We define like a call routine to neural model itself. So we call itself. What the call routine do is that we take out some input and we generate output from that. So the input we're taking here is a target word, and the context of that target word, and that is from the pair information that we receive from model. So we get equal to pair. We're generating the embedding layers, the word embedding layers, right? That is the target embedding that we define up there with the target. So we can encode the target word itself. And for the context embedding, we just use the context embedding layer that we define. But this time with the context, so that we can like encode the context words. We dot them, calculate the dot product, dots of the context embedding and the word embedding, so we know how similar each target word to the context word are, so that we can know how to classify them as being close or not, right? And return the flattened versions of the dot product. Now that run model. Okay, this here we got an error because we haven't defined a model. But now we define the model, we will no longer get that errors. We set the embedding dimensions here as 128. So originally each vector is like, each word vector will be like 1,000 units long or more, right? But now getting out this each vectors root vectors, we have like a length of like 128, encoding more meaningful information than sparse vector. And now we train the model. For loss function, we just use categorical cross entropy because it's like we're getting it from logit, right? We're just calculating the raw score, which is unnormalized for the model. That's why we have to set from logit to true, and we use categorical cross entropy because we are having like five vectors, have 5 labels to classify at once. Okay, so we just define to log training statistics, and then we feed the model. And here we just, at this point, we just wait for the model to just finish training itself. And while it is training, we take a look at the rest of the code, right? So at this point, we just extracting all the embedded train vectors from here. And we download it as like a metadata file and a vector file. And so while we're waiting for it to train, we just take a look at like yeah, it's taking a bit to train. Okay, so here is what we're going to use to visualize what like the vectors that we trained before, called the embedding projectors. I can just post a link here, so when everyone got the files, they can put in and see what kind of words they get for. Put in a chat. Just have it 2D, easier to look at. Okay. Why are we waiting for our model to train? Yeah, it's getting more and more accurate. Everyone have any questions so far? All right. Okay, so I'm gonna finish training. We can take a look at some of the training statistics here, seeing that accuracy is increasing, the loss of more is decreasing. That our root vector is being fitted pretty nicely. Alright, and we visualize that in TensorBoard. See a nice curve here, getting closer to perfection. Alright. So now that we are already trained the models, we just get the weights for the models and we use them to look at what we have. Like, alright. We have them up so we can put them in the visualizer. The vector files is a bit big because we're downloading every single vector, so every single word in the vocabulary. So that's gonna take a while. Alright, so here we just load the data from model. Load TSV file vectors, right? We can just load it here. These are vector files where we have the actual word vectors and the file metadata, which has the list of words according to each vectors. Vectors, metadata. Alright, so here is our visualizations of what we train. It is a very confusing clouds of points, right? If we click just one thing, entangle, right? You can see that here are the list of words that's like most similar to it. Count it, but like how similar to it is, and you can see here this belief is really close to entangle, suggesting that there might be some kind of similarity, right? Let's take a look at like another word, bedroom. Okay, why is bedroom similar to Spain? That's a good question. Why is calculation similar to bedroom? Maybe word piece have some kind of weird things that we don't know. Or encountering is really similar to linking, which is very interesting to intersect, which is like kind of like, oh yeah, we're just being together in some way or another, right? Alright, just rambling, sorry. Rusty, scar. This is one of very good example. You can see that rusty here is really close to scar, and we can all see what the similarity them is, right? Alright, so that's a visualization of how vectors turns out to be, and that's about it. And so to conclude, what's our embeddings? Okay, wait a minute. So embedding is a way to represent text data in a meaningful manner for computers, and it is similar to how images are represented by pixel values as data. And it is an efficient way to vectorize like non-numerical data, capturing what we care about documenting text. Part of word meanings characterized like by word similarity and relatedness, right? And the type of what we've seen so far is the static embedding. There's a more advanced way to create word embeddings called contextual embeddings, which change how the word is represented depending on the context of the word itself. So if you have a word in different sentences, you have different embeddings. And why are embedding important? Remember that embeddings are learnable, right? So they can be adapted to any downstream task, and should it be sentiment classifications or summarization, and the model learn the word representations that's most meaningful for that certain task, and change word representation to store that information. And BERT is a pre-trained model that uses a kind of embedding called word piece embedding, and also BERT is a very sophisticated language model that we're going to take a look down the line in this workshop series. And that's the end of our workshop. Special thanks to the AIS team for giving us opportunity to bring this content to you. And the workshop is an adaptation of the material from textbook Speech and Language Processing. And it's a very wonderful textbook. And if you like, but if you care about NLP, you should probably check it out. On the next workshop of the series, we'll take a look at one of the fundamental building blocks of modern NLP, which are deep learning techniques for text sequence processing. And once again, thank you for coming to a workshop. Please let us know about a workshop, what you like about it, what you can improve on, and we'll post the survey links later on down the lines. Thank you for coming.